Hi, this is Ifan, and I'll be presenting on my research project, CNOT-Optimal Circuit Synthesis. So first, what is a CNOT gate? In computer science, we work with functions that have binary inputs and outputs. And a CNOT gate is a function which takes in binary inputs x, y, and outputs x and x XOR y. So we have this XOR table, which is basically addition under mod 2. So the only difference with of x XOR y between x plus y is that when x and y both equals to 1, x XOR y becomes 0 instead of 2 because we're doing mod 2. And this is how we visualize a CNOT gate in a quantum circuit. Then a CNOT circuit is a circuit that only consists of CNOT gates. So for example, this is a CNOT circuit. And we can extend it, adding more CNOT gates. So this is also a CNOT circuit. And in this CNOT circuit, we have two CNOT gates from the first bit to the second bit. So it'll end up be the same results. Now, if we add another gate from 2 to 3, then we'll add x2 to x3. Despite looking different, we might have noticed that some CNOT circuits are indeed equivalent. So, for example, in our previous example, we have a CNOT circuit C with 3 gates. However, we can realize it with only 1 gate. And despite that they look different, the input and the output is like completely the same. If you have the same input, you will have the same output. So now we have our motivating question of our research is that given the CNOT circuit C, what is the minimum number of CNOT gates needed to construct such C? And now we introduce some other notions. So sometimes we can only use CNOT gates between certain pairs of inputs. So for example, we have this constraint, which means that we can only use a CNOT gate from 1 to 2 and from 2 to 3. Or we can build a CNOT circuit using the combination of the previous two CNOT gates. However, what we cannot do is building a CNOT gate from 1 to 3 or from 2 to 1. So now it comes to our problem statement, which is given the CNOT circuit C, a topological constraint S, and an integer k. We want to determine if there exists a CNOT circuit equivalent to C such that it has at most k gates, and it only uses CNOT gates in the constraint. And we will refer to this problem later as MCCSP. Our main result is that this problem is hard to solve efficiently, or more formally, it is NP-hard. What problems are hard to solve efficiently? So computational complexity measures the difficulty of finding a solution. For an input of size n, if we can solve the problem in polynomial time, this is fairly efficient. However, if it takes exponential time to run, it's not very efficient. So for example, we can see that in this graph, the red line is like linear time, and the other two are like exponentials. So they increases really fast, and basically you won't expect getting a solution when the input size increases to like 100 or 1,000 or even bigger. And the main technique we use in our proof is called reduction. So how do you prove that a problem is hard to solve efficiently? First, we can choose a problem A, which is hard to solve efficiently. Then we can show that if B can be solved, then we can use the solver that we found for B to solve A. And this brings us a contradiction, which means that B cannot be solved efficiently. And the hard problem A that we found is called vertex cover. So the definition of a vertex cover of a graph is some subset of vertices such that any edge in the graph touches at least one vertex in the vertex set. in the vertex cover. So for example, in the graph we have here, 1 and 3 forms a vertex cover since it covers all the edges 1, 4, 1, 3, 1, 2, 3, 4, and 3, 2. However, it can be proven that like for the graph above, it is impossible to have a vertex cover of size 1. So it's impossible to cover the whole graph using only one vertex. And the vertex cover problem is asking if there exists a vertex cover of size at most k. If it's impossible, then we output no. So we want to determine if there exists a small enough vertex cover. And vertex cover problem is known to be hard to solve. And step 2 is that we have a reduction from vertex cover to MCCSP. So right now, suppose that we have already found a solver for the MCCSP. All we need to do is that we need to find an efficient reduction to transform the input to vertex cover problem to the input to MCCSP problem, so that we know that if the reduction works and the solver works, then we have an efficient vertex cover solver. But that is proven to already be like vertex cover is already proven to be hard to solve, so that we reach a contradiction. So, and the key property of the reduction is that it has to satisfy that if the input is a yes input of the vertex cover, then after the transformation of the reduction, it becomes a yes input of the MCCSP. If it's a no input, then it becomes a no input of MCCSP. And our main result in this research is that we built an efficient reduction from like the input of vertex cover to the input of MCCSP, so that we prove that MCCSP is NP hard. And we conjecture that our proof can generalize to undirected topological constraints, which means that if Ij is an allowed CNOT gate, then so is Ji. That's all for now. I would like to thank my mentor Henry Ma, my tutor Peisho, and Dr. Tanya Kovanova and Professor David Jarrison. I would also like to acknowledge RSICE and MIT for supporting me throughout this research project. Thank you.